Okay, here we have an exponential decay problem. So we have a substance that's decaying at a certain rate, and we first write down our exponential decay or exponential growth function. And we have to figure out C and K based on the information in the problem. So let's start with this phrase. It says initially there is 100 grams of the substance. That means when t equals 0, y is equal to 100. So let's use that information, and we'll use that information to find C. Okay, so we have 100, y is equal to 100, when t is equal to 0. This is e to the k times 0, which is e to the 0. E to the 0 is 1. So we get c is equal to 100. So let's rewrite our function. We have y is equal to 100, e to the kt. And now we want to find this constant k. So we use this information. The substance has a half-life of 1,200 years. That means that when t is equal to 1,200, y is equal to half of the initial amount, half of 100, or 50. All right, so in other words, 50 is equal to 100 e to the k 1,200. Divide both sides by 50, and we have 1/2. 50 over 100 is 1/2. 1/2 on the left-hand side. And now we want to figure out what k is, so since it's in the exponent, we'll take the log of both sides. So let's do that. So we have the log of 1/2 is equal to, now when we take log e to something, we just get the exponent. So remember, log and e are inverses. So there we have k right there. Log 1/2 over 1,200. And finally, what we're going to do is answer the question. After 300 years, how much remains? Okay, we can, well, let me just say we can approximate this. I get minus 0.00057776. All right, so now we want to substitute in t equals 300 and see what y is. Okay, that just would answer our question. So y is equal to 100, that's c, e to the k, so we have this constant over here. And t is 300. And we just do this on our calculator, and we get that y is approximately equal to, I'll do it over here, y is approximately equal to 84.0896, and that would be grams. We're going to differentiate this log expression, and before we do that, we're going to take advantage of the log properties and expand this expression so that we don't have to use a product rule or a quotient rule. Okay, so let's do that. So we have y is equal to 10 log x squared plus 3 plus 1/2 log 2x plus 1 minus 5 log 3x minus 2. Now we're ready to differentiate. So we have dy dx is equal to 10 times, all right, the derivative of the log of an expression is 1 over that expression times the derivative of the expression, so that would be, that's a chain rule, 2x in the numerator. Okay, continuing on, we have 1/2. And then 1 over 2x plus 1 times 2 minus 5. And then we have 1 over 3x minus 2 times 3. And that's the derivative. Okay, we want to differentiate this expression, or this function, and we want to take advantage of log properties even though this is not the log of an expression. We don't have the log here. This isn't a log function, but we still want to take advantage of log properties in order to expand this expression. So we can do that using what's called log differentiation. We start by taking the log of both sides of the function. So we have log y equal to, and on the right we have the log of 3x plus 5 to the 8th over this square root. And now let's expand using log properties like we did in the previous example. So we have 8 times the log of 3x plus 5 minus 1/2 log 2x minus 7. So now this right-hand side is easier to differentiate. Let's differentiate both sides. On the left, we use implicit differentiation. All right, so we have 1 over y times the derivative of y, that's y prime over y, is equal to, and on the right we have 8, and then 3x plus 5 in the denominator, times the derivative of 3x plus 5, and then 2x minus 7 in the denominator, times the derivative of 2x minus 7. All right, now this isn't quite y prime. This is y prime over y. To get y prime, we're going to multiply both sides by y. So on the right-hand side, I'm going to have y, and instead of putting the variable y, I'll put the expression that y is equal to. So I'll put that here. So this is y. And I'm going to multiply all that by the right-hand side in the line above. Okay, this is 24 over 3x plus 5 minus, I'll cancel those 2's. Okay, so that's the derivative, and we took the derivative without using the quotient rule. In number 4, we're asked to use log differentiation to differentiate this function. Whenever we have x in the base and x in an exponent in some sort of exponential expression, then we have to use log differentiation. Okay, so we'll start by taking the log of both sides. So we have log y is equal to, and I'll bring the 5x down right away, taking advantage of the log properties. Okay, now we'll differentiate both sides. On the right-hand side, use the product rule. So here's the first times the derivative of the second. Okay, put this in the denominator. The derivative of this expression goes here. And then we have the derivative of 5x is 5 times the second function. Okay, now just solve for y prime. So y prime is equal to y times this right-hand side over here. I'm going to just multiply top and bottom by x squared just to simplify this. So here I get 1, here I get x squared, minus x. Okay, so that's the derivative. That's y prime. Okay, let's differentiate these two functions. So in the first case, we're going to use a product rule. And we have the first, that's x squared, times the derivative of the second. Okay, so that would be 1 over 1 over x times the derivative of 1 over x, and we'll be simplifying that soon. So that's the first times the derivative of the second, plus the derivative of the first, that's 2x, times the second. And that's really it, but let's simplify this. We have x squared times 1 over x squared, that's a minus 1 in front. All right, so that would be a minus 1, all this is minus 1 in the numerator, and 1 over x in the denominator is the same as x. So all this simplifies to minus x. Okay, so that's dy dx for A. And for B, we're going to use a product rule as well. So we have the first times the derivative of the second. Now the derivative of 3 to the 5x, well, first we have log 3 times 3 to the 5x times the derivative of 5x, which is 5. All right, so all this is the derivative of, all that is the derivative of 3 to the 5x. All right, so that would be the first times the derivative of the second plus the derivative of the first times the second. Okay, now we're going to find some max, min, and inflection points of y equal x squared over 2 minus log x. So remember, max mins are found at critical values, that is, where the derivative is equal to 0, or where the derivative doesn't exist, but the function does exist. But in any case, in this case, it's just going to be where the derivative is equal to 0. That's where we'll look for the max mins. So let's find the derivative. Okay, so the derivative of x squared over 2, that's x, minus the derivative of ln x, that's 1 over x. All right, now we want to set this equal to 0 and solve. Let's add these two together. Okay, so that's getting the common denominator of x. That's x squared over x minus 1 over x. And that's x squared minus 1 over x. All right, we want to know where is this equal to 0. So that's equal to 0 where the numerator is 0. That is when x is equal to plus or minus 1. And the derivative doesn't exist when x is equal to 0. But notice this function over here is only defined for x greater than 0. Because ln x is defined, the domain of ln x is x greater than 0. Okay, so let's do a plus minus analysis of y prime. That is, let's see where y prime is greater than 0, less than 0, or equal to 0. Well, it's equal to 0 when x is equal to 1. We won't count x equal minus 1 because remember the domain is only x greater than 0. So the only critical value here is x equal to 1. That's a critical value where the derivative is equal to 0, not x equal minus 1 because it's not in the domain. All right, so this actually starts at, this line will start at 0, or to the right of 0, not including 0. Now let's do a plus minus analysis. So we're going to evaluate y prime to the left of 1 and to the right of 1. All right, let's say to the right of 1, let's say if we substitute in 2, for example, we have 4 minus 1 over 2, which is positive. So y prime is positive to the right of 1. And to the left of 1, if we substitute in the value between 0 and 1, let's say 1/2, well, here we have 1/4 minus 1, which is negative, over 1/2, which is positive, so that would be a negative quotient, so that's negative. Okay, so that tells us that y prime is decreasing to the left of 1 and increasing to the right of 1. Sorry, not y prime, but y. Y is decreasing. Y prime is negative, so y is decreasing here. And here, y prime is positive, so y is increasing. And that makes 1 a minimum. Decreasing, increasing, decreasing to the left, increasing to the right. 1 is a minimum. So that's our 1 max-min point. Substitute in 1, and we have 1/2 minus the log of 1. The log of 1 is 0, so that would be 1/2. So we have a minimum at 1 comma 1/2. And now to find inflection points, we take the derivative once again. Okay, let's take the derivative of y prime in this form. So let's look at that. Y double prime is equal to 1 minus the derivative of 1 over x, which is minus 1 over x squared. So that's 1 plus 1 over x squared, which is always greater than 0. We have this quantity squared plus 1. It's always greater than 0. So we have no inflection points. Okay, the second derivative is never 0, so we have no inflection points.